Now that we've discussed what functions are and how they relate to graphs, let's sketch some typical graphs. So one typical graph that we've already seen before is a linear function, right? So a linear function is exactly as it sounds, linear. It relates to lines, right? So a linear function might do something like this. And this will be y is equal to mx plus b, where this is the x-axis, this is the y-axis, right? The slope m will tell you how steep it is. If this is a very big number, then it'll be very steep. If this is a small number, then it'll be flatter, right? If the slope is 0, then it will be a horizontal line, right? If the slope is negative, then it'll be sloped down like this, right? Okay, so this is just a typical linear function. The nomenclature would be linear. Right? The next graph that we should be aware of is called a quadratic function. So let's sketch the graph like this. This will be y is equal to some constant c times x squared, right? And so c is any constant, and if c is a very small number, right? If c is, say, less than 1, let's say c is 1/2 or 1/4 or 1/5, then the graph will start to open up like this, right? And it'll be flatter, okay? But if c is a bigger number, c is 50, 75, 100, then the graph will become steeper and steeper like this, right? Because the function will be climbing faster, right? So this is the typical graph, right, that shows up, and this would be considered quadratic, would be the nomenclature used, quadratic. Okay, the next graph that we'd like to take a look at is the cubic. Right, so cubic will come up from the negative x values and will go up like this, right? Now, of course, they're understood to be arrows and all these, meaning that they extend to infinity in their respective directions, right? So it comes up, right, and then it levels off. The slope, actually, I didn't draw this amazingly well because the slope for a cubic is actually 0, right? At the origin, the slope is 0, and then it curves back downward like this. And so this is y is equal to some constant c times x cubed, like this. So see that if that constant is very big, then it will be much steeper, right? But if c is very small, if it's, say, less than 1, 0.5, 1/4, 1/2, 1/4, 1/5, 1/6, then this thing will be, it would do something like this, right? It'll sort of flatten out more, right? Okay, and this is said to be cubic. And we'll write it right here. Okay, next graph that we'd like to discuss is the exponential functions. So this will be y is equal to, let's just sketch it here first. Y is equal to some constant c times some number, but then that number is raised to the x power, like so. Right? And now this right here, this y-intercept will be c, because when x is equal to 0, any number, whether this be 1, 2, 3, the natural logarithmic number e, which is a number we'll see later, e is equal to, or approximately equal to, 2.71828, and then it goes on, right? But if whatever this number is, right, the bigger this number is, then the steeper it will be, right? But then if it's raised to the 0 power, then whatever that number is, this whole quantity, anything raised to the 0 power is 1. I don't care if it's a million raised to the 0 power. A million raised to the 0 power is 1, right? So then at the x-axis, when x is equal to 0, this will be whatever that constant is out in front, right? And so these are the exponential functions. If this constant is bigger, right, then it'll be steeper like this, right? Obviously, also, if this number is bigger, then it will be steeper as well, right? And then it's asymptotic on the back side. It's asymptotic in this direction. That is, it approaches the x-axis and it gets very, 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 very small very fast out here, right? Okay, then the next function we would like to discuss is the square root function. So these are just some typical graphs that we all need to be aware of, how they look and how they behave, because these show up, right? These show up more frequently than others. So this will be, and again I just need to put the arrow here. This will be y is equal to square root of x, like so. Okay, so then we know that, because this is equal to the square root of x, look, the graph doesn't exist on the negative x-axis. That makes sense because you can't take the square root of a negative number. It's imaginary, right? So you can't plot that. So the graph doesn't exist out here. In fact, we would say the domain of this guy will be, and 0 will be included in the domain because square root of 0 is 0, so then it's 0 out to infinity, because you can take the square root of any really big number, square root of 1,000,000, square root of 2,000,000, it's going to be actually something, right? The domain of this guy, I'm going to put it with a d like this, is negative infinity to infinity. Domain of this guy is negative infinity to infinity. And the domain of this guy is also negative infinity to infinity, right? And similarly for this guy. While we're at it, let's do the range. The range of this guy will be from negative infinity to infinity. We always put the curved bracket for whenever the infinity is involved, right? Can't actually reach infinity. And then the range will be, now the range will not be negative infinity. It'll be a square bracket at 0, because look, it only exists in the y direction. It only exists above this part right here. So this will be 0, comma, and then it does go to infinity on the positive y-axis, right? The range for this guy will be negative infinity to infinity, right? Because it goes negative infinity and it goes positive infinity in the y direction. And the range for this guy will be 0, open bracket, because this is asymptotic, meaning that it never touches but becomes infinitesimally close way out here, right? So it's open parentheses, right, comma, positive infinity, right? Because it does increase up to infinity, right? That's the range. And then for this guy, the range is the same as the domain, right? Okay, last one will be, oh, did we do that one? No, we did not. So there'll be two more. This will be the natural logarithmic. And the natural logarithmic will do something like this. Let me redraw that one. Try to draw that one a little bit better. It looks sort of square rootish, right? Except that it crosses the x-axis here. And then this is at the number 1. Natural log of 1 is equal to 0. So this is y is equal to natural log of x, right? Let me write that a little bit clearer. Okay? And it's asymptotic at the y-axis, so it never touches the y-axis, but it becomes very close. So then the domain for this guy is open parentheses from 0 to positive infinity. And the range, what do you think the range is? Look, this guy goes all the way down that way, and it just keeps climbing in this direction. It's got a little bit of a slope all the time. So this is from negative infinity to positive infinity. The range, yeah, that's right. Okay, so these are just some typical graphs and some nomenclatures. This is natural logarithmic. This is the natural logarithmic. And you could, logarithmic graphs behave quite similar as well, right? You have to forgive me if logarithmic is spelled incorrectly. It's not mathematics, so we're not concerned with it. And then this is just a square root, right? And this is the exponential. Okay, so these are just some typical graphs that will show up frequently. These are some nomenclatures that we should all be familiar with. If you need some flashcards or something, this is a useful idea. But you should be, just sort of familiar in general with these functions and how they behave. I'm going to step out to the side and give you a clear screenshot. Good opportunity to pause the video and just take a look at them and just sort of process them. I'm going to step to the side.